I'm not feeling really well, so excuse me if I cough in between. I'm Abhinav, and I'm going to talk about testing submodularity. This is joint work with Eric Blay. Let me start by defining submodular functions. A set function is called submodular if for every pair S and T, when you add an element to both the sets, then the increase would be greater when you add it to the smaller set. This property is called property of diminishing returns. And here the input, instead of as sets, could also be viewed as binary strings of size n. So the functions would be from the hypercube to the real set 0 to 1. Submodular functions show up everywhere. Utility functions in economics, cut functions in graphs, entropy of variables. So the bottom line is submodular functions are really important. A very basic question to ask would be, could we test submodular functions? Like, given a submodular function, could you determine if it is submodular or not? Or if you can, how efficiently you can do it? Testing submodularity studies that. And for us, the universe of functions is all the functions from the Boolean hypercube of dimension n to the real set 0 to 1. And we are just looking at submodular functions. An algorithm for testing submodularity should accept every submodular function with probability greater than 2 over 3 and reject every function that is epsilon far from every submodular function with probability 2 over 3. This is a picture of testing submodularity. Let's look at the formal definition. An epsilon submodularity tester in L2 testing model is a randomized algorithm that, given oracle access to function f, accepts with probability 2 over 3 if f is submodular, and rejects with probability 2 over 3 for every submodular function g. The distance between f and g is greater than or equal to epsilon. For this talk, when I say distance, I mean the L2 distance, and the testing model we'll be looking at is L2 as well. The algorithm we have would work for general LP, but to keep it simple in this talk, we'll be looking at just L2. So the question we'll be answering in this talk is, what is the minimum number of queries required to epsilon test submodularity? A trivial tester would be to query the function. So we would like to minimize the number of queries. A trivial tester would be to query the function at all the inputs, and that would require 2 to the power n inputs. Sorry, 2 to the power n queries. So could we do better? Feldman and Vondrack showed that there exists a epsilon submodularity tester with the following query complexity. The thing to note in the query complexity is it has logarithmic dependence on n, so which is already a doubly exponential improvement over the trivial algorithm. They achieved this by proving something stronger. They proved that submodular functions are close to juntas. You call a function k junta if it is dependent on only k number of variables. The theorem they prove is every submodular function f is closer to another submodular. There exists another submodular function g such that f and g are epsilon close, and g is a junta over 1 over epsilon square junta. So what this theorem says is every submodular function can be approximated by another submodular function which is dependent on very few variables. So that's what this theorem says. And here is the testing algorithm, like brief outline. They first assume that the given function is submodular, and then learn the variables of the junta the function is close to. And once they learn the variables of the junta, they learn the junta on these variables. And once they learn the junta, they check if it's submodular and close to the function you have. Steps 2, 3, and 4 are pretty much straightforward once you have the theorem that submodular functions are close to juntas. So, great, we have a log n query complexity tester. So what's the next question we could ask? Could we do better? could we test using constant number of queries, the number of queries independent of the dimension n. So interestingly, like in previous approach, if you want to learn what the variables are exactly, then using information theoretic bounds, you can show that you cannot do better than log n. But that does not mean we cannot test in constant number of queries. So in this paper, we show that you can test submodularity using 2 to the power 1 over epsilon square queries. We achieve this by devising a testing by implicit learning algorithm. Testing by implicit learning is a very powerful technique which has been used to get constant query testers for many properties of Boolean functions. But all the existing techniques have the following limitations. They work only when the function is epsilon close to a really, really small junta. So the junta size has to be at most 1 over root epsilon. This clearly wouldn't work in our case because the junta size is 1 over epsilon square for submodular function, which is clearly much larger than this. And one other limitation of these algorithms is they work only in the Hamming setting. So in our algorithm, we get rid of this dependence on epsilon. So our algorithm would work even if the size of the junta is 2 to the power 1 over epsilon or 2 to the power 2 to the power 1 over epsilon. And also it would work for a general LP testing model. So here's the brief outline of our algorithm. First, we start by generating 2 to the power k samples, where for submodular functions k is 1 over epsilon square. And with the help of these samples, we partition the variables into so many buckets. How we do this is 2 variables go into the same bucket if they take the same value on all the samples. So at the end of partitioning, so all the variables in the bucket would be taking the same value on all the samples. For people who are already aware of the testing by implicit learning algorithms would recognize this is different from what the usual algorithms do. And once you have partitioned the variables into buckets, the next step would be to identify a set of k buckets. This we do by process of elimination, such that all the variables in rest of the buckets together have very low influence. And once you identify the set of k buckets, we accept the function if there exists a submodular k junta that is close to the function f on these samples. Along with a constant query L2 tester, we also get a constant query LP tester with the following query complexity. And we also get constant query testers for the following functions: XOS, OXS, unit demand, coverage, and self-bounding functions. And in the future, if somebody comes up with a theorem that some function class X is close to juntas, then they would be getting a free testing algorithm too. So that's it.
Is there some what's the intuition for why they're close to juntas? Is that obvious? Why these submodular functions should be close to juntas? Or is that
It's I think it's not obvious. It was a big breakthrough result in 2013.